Hi everyone, I'm Chu-Pan. In this talk, Leo and I are going to present our work on efficiently finding higher-order mutants. This is a joint work with Jens, João, Christian, and Eduardo. As background, mutation analysis is a line of research that injects faults into existing programs for different goals, such as assessing the quality of a test suite or evaluating for localization techniques. Traditional approaches to mutation analysis use first-order mutants, meaning that each mutant applies only one change at a time, such as the example below. However, there are also higher-order mutants, which contain multiple changes at once, such as the example on the right, where two operators are modified at the same time. Higher-order mutants are not commonly used by practitioners or researchers, largely because there could be exponentially many higher-order mutants if we combine first-order mutants randomly, and studies have shown that not all higher-order mutants are useful because some of them might be easier to kill than first-order mutants. Jia and Harman have systematically investigated different types of higher-order mutants in their studies, and they found out that a specific type called strongly subsuming higher-order mutant can be beneficial. The central idea behind using strongly subsuming higher-order mutants is that they are harder to kill than normal first-order mutants. Let me give you such an example. We start with a very basic program. From this program, we can easily generate two first-order mutants by changing different operators one at a time. And if we apply the two mutations at the same time, we can get a higher-order mutant. Let's further assume that we are using these mutants to evaluate the quality of a test suite, in particular, these three test cases, all of which should pass the original program. For mutation 1, two test cases fail. For mutation 2, different two test cases fail. Now let's look at the higher-order mutants. Existing studies show that some higher-order mutants are easy to kill, so you might expect a case like this, where the higher-order mutant fails even more test cases than the first-order mutants. But actually in this case, the higher-order mutant is harder to kill. Interestingly, for the higher-order mutant, only one test case fails, the same test case that failed for mutation 1 and 2. And if you look carefully, you will see that mutation 1 and 2 somehow interact in the control flow to mask each other's faulty behavior to make test 2 and 3 pass. As we can see, the higher-order mutant is more subtle and harder to kill. Recall that in mutation testing, we want to generate hard-to-kill mutants, so that we can evaluate and improve the quality of a test suite. For this reason, hard-to-kill mutants like the higher-order mutant we are showing here could be useful for mutation testing. You can find a formal definition of strongly subsuming higher-order mutants in our paper or in earlier studies, but intuitively, they are made of first-order mutants that interact in such a way that the strongly subsuming higher-order mutant is more subtle and harder to kill. Studies have shown that strongly subsuming higher-order mutants have several benefits, such as increasing test effectiveness, increasing test efficiency, and reducing the likelihood of being equivalent mutants. The problem is, they are difficult to find in an exponentially large search space of first-order mutants. This work targets this specific technical challenge. Again, the goal of this work is to find strongly subsuming higher-order mutants efficiently. We take a three-step approach. In the first step, we use a technique called Variational Execution to search for strongly subsuming higher-order mutants. While using variational execution is much more effective than previous approaches, existing implementations might not scale to larger programs. So in the second step, we study basic characteristics of strongly subsuming higher-order mutants. And in the final step, we design a new prioritized search based on the characteristics we identified. In the rest of the talk, we will walk you through each step. Let's begin with step 1, variational search. The secret sauce of this search strategy is an existing technique called variational execution, which is a dynamic analysis technique that is typically used to study interesting interactions among a set of options. In our case, options are first-order mutants, and their interactions make strongly subsuming higher-order mutants. Variational execution can tackle exponentially large search spaces by exploiting sharing among similar executions. For the interest of time, I'm not going to fully explain how variational execution works. But for this presentation, it is sufficient to think of it as conceptually similar to symbolic execution, where common values and executions are shared by using some form of abstract values and path conditions. The main difference is that variational execution performs concrete execution underneath rather than symbolic reasoning. Let me give you an overview of how we use variational execution to search for strongly subsuming higher-order mutants. First, as a preparation step, we generate all first-order mutations in a program using common mutation operators. We then encode all the first-order mutations into one metaprogram so that we can use variational execution to explore different combinations of them. In the example shown below, we encode two mutations by expressing them as conditional expressions, where the conditions are Boolean variables that control whether or not a mutation is applied. Next, we use variational execution as a black box technique to run the metaprogram against an existing test suite. For each test case, variational execution will output a Boolean condition that represents which combinations of first-order mutants cause the test to fail. We transform these conditions into a formula that bakes in the definition of strongly subsuming higher-order mutants. This way, we convert the search of strongly subsuming higher-order mutants into a Boolean satisfiability problem, which can often be solved efficiently with BDDs or off-the-shelf set solvers. Each solution to the Boolean satisfiability problem corresponds directly to a strongly subsuming higher-order mutant. And if the set solving terminates, we are guaranteed to find a complete set of strongly subsuming higher-order mutants with regard to the test suite and mutations. The main challenge in this approach is to construct a formula that represents all valid strongly subsuming higher-order mutants in the search space. In our paper, we detail how we transform the output of variational execution into a set problem. For the interest of time, we are going to skip the details in this talk.
We evaluated our variational execution approach against the state-of-the-art genetic algorithm search, as well as a naive baseline exhaustive search. We ran these 3 searches on 5 programs: Triangle, which is a small program commonly used in mutation testing work, as well as 4 programs used in the largest previous study on finding strongly subsuming higher-order mutants. These programs range in size from 19 lines of code to 7,000, and the largest of these programs contains around 2,000 first-order mutations. We first evaluated the exhaustive search on Triangle. The exhaustive search simply checks each possible combination of first-order mutants, starting from order 2, then 3, and then 4, until the search times out. Through the behavior of the tests, we check whether each combination is a strongly subsuming higher-order mutant. This plot shows the number of strongly subsuming higher-order mutants found over time, and we can see that the exhaustive search is able to find most of them in 12 hours. We then ran the genetic algorithm, which is the current state of the art, and aims to genetically select for combinations of mutants that are more likely to be strongly subsuming. Here, we can see that the genetic algorithm can find more strongly subsuming higher-order mutants in a shorter period of time. Finally, we compare these results to our variational execution approach. The behavior of the variational execution approach is very different from the other 2 approaches. First, there is a period where no strongly subsuming higher-order mutants are found. During this period of time, variational execution is running on all the first-order mutants in the program. Around the 40-second mark, there is an almost vertical spike in the number of mutants found, as once we have the information from variational execution, we can very quickly obtain solutions from the BDD. Finally, we can see that after the spike, we are guaranteed to have found all the strongly subsuming higher-order mutants in the program with regards to the tests and the mutations used. We can see that the variational execution approach is able to find all the strongly subsuming higher-order mutants in a much shorter time period than the other approaches. We observe similar patterns in other subjects. Here, we have monopoly. the existing approaches find less than half of the strongly subsuming higher-order mutants in 12 hours, but variational execution is able to find them all in about an hour. We can also see in CLI that variational execution can find all the strongly subsuming higher-order mutants in a matter of minutes. The results show that using variational execution is promising. However, similar to symbolic execution, existing implementations might not scale to large programs. Because of this, we ultimately want to have a more lightweight approach to finding strongly subsuming higher-order mutants, and in order to get there, we need to learn more about what they look like. Since we have now fully enumerated the strongly subsuming higher-order mutants in various programs, we have the unique opportunity to identify common characteristics without the risk of a potentially biased sample. We were able to identify 4 basic characteristics that strongly subsuming higher-order mutants tend to exhibit. First, they are often composed of only a few first-order mutants, a characteristic we term mutation order. Second, most strongly subsuming higher-order mutants are composed of first-order mutants in the same method, and they rarely span multiple files. We call this characteristic proximity. Third, they are often composed of first-order mutants that are killed by the same set of tests, a characteristic we term equivalent test failures. Finally, adding a first-order mutant to an existing strongly subsuming higher-order mutant can often form a new one. We call this characteristic containment relationship. Based on these characteristics, we developed a prioritized search to allow us to scale to larger programs. The prioritized search is intended to be an exploration of potential strongly subsuming higher-order mutants based on the identified characteristics, as opposed to the variational search, which aims to explore all possible strongly subsuming higher-order mutants at once. The prioritized search is intended to be lightweight and thus scalable, but not complete, while the variational search is much more heavyweight, but is guaranteed to find all strongly subsuming higher-order mutants for smaller programs. The prioritized search is similar to the existing genetic search and exhaustive search in the sense that we check higher-order mutants one at a time, but our search strategy prioritizes higher-order mutants that match the 4 characteristics we outlined. We use the proximity characteristic to narrow the number of candidate higher-order mutants to those made up of first-order mutations within a package. The penalty function for sorting the candidate higher-order mutants utilizes the other 3 characteristics, as it is a linear combination of the mutation order, the number of test outcomes that differ between the first-order mutants, and whether or not it has a containment relationship with a previously found strongly subsuming higher-order mutant. We then evaluated our prioritized search against previous searches, including the variational search, exhaustive search, and genetic algorithm. The prioritized search outperformed the exhaustive search and genetic algorithm in most of the projects, and as you can see here, in Monopoly, the prioritized search was even able to outperform the variational execution approach. We also evaluated the prioritized search on projects that were too large for variational execution. For example, we have JFree a project with 90,000 lines of code and 36,000 first-order mutations. The prioritized search found over 576,000 strongly subsuming higher-order mutants, while the exhaustive search and genetic algorithm found none in the allotted time. We see the same thing in math, an even larger project with 104,000 lines of code and 103,000 first-order mutations. Here, the prioritized search found over 390,000 strongly subsuming higher-order mutants, while the exhaustive search found none, and the genetic search was only able to find at most 2 in our trials. There are more detailed results in the paper. In conclusion, in order to find strongly subsuming higher-order mutants, which are useful for mutation testing, we created a variational search that allows us to completely enumerate all strongly subsuming higher-order mutants in small to medium-sized programs. We studied those strongly subsuming higher-order mutants to identify 4 basic characteristics, and we created a lightweight prioritized search that is able to identify strongly subsuming higher-order mutants in large programs and significantly outperforms existing methods. Thank you for watching, and let us know if you have any questions. Finally, the software engineering program at Carnegie Mellon is looking for PhD applicants this fall. If you are interested, contact us.